Hello, everyone. I am Shixun Huang from National Kaohsiung University of Science and Technology, Taiwan. Today, I want to talk about O2 algorithm, which is a kind of global thresholding. O2 algorithm was firstly published in IEEE Translation on Systems, Meant, and Cybernetics in 1979, and it is widely used in the computer vision area. The outline of this lecture includes introduction about the definition and the formulation of global thresholding, class separability measure about the criteria used in O2 algorithm to measure the goodness of the threshold value, threshold selection algorithm about the implementation detail of how to select an optimal value for thresholding. What is thresholding? Thresholding is an operation to assign a binary value 0 or 1 to each image pixel f of sy according to a threshold value t star. If fsy is less than or equal to t star, the output g of sy is 0. Otherwise, g of sy is 1. Next, what is global thresholding? Global thresholding means that the value t star used for thresholding is a constant over an entire image and is independent of pixel location and neighbor information. Here shows an example of applying thresholding using t star equal to 3 to an 5x4 image with 8 gray levels. The pixels with gray level less than or equal to 3 are all assigned to the output label 0. The others with gray level larger than 3 are assigned to label 1. Hence, the main issue to be addressed in global thresholding is how to select a good threshold value. O2 algorithm is thus a way to find an optimal threshold for global thresholding. Here, we firstly give the formulation of global thresholding problem. Let pixels of an image be presented in yellow gray levels, ranging from 0 to L-1. Define normalized histograms of an image with yellow levels as P0, P1 to P sub L-1. Pi is the ratio of pixels with gray level equal to I and is defined as Ni over N. Ni is the number of pixels at gray level I. Big N is the total number of image pixels. The objective of O2 algorithm is to find an optimal threshold value t star subject to a class separability measure, which will be mentioned later. The selected threshold t star is then used to dichotomize pixels into two classes, C0 and C1. Pixels with gray level from 0 to t star are in C0 class. Those with gray level larger than t star are in C1 class. For this 5x4 image, this picture shows its normalized histogram. Because there are no pixels with gray level 0, P0 is 0 over 20. Because there are 4 pixels with gray level 1, P1 is 4 over 20. With this normalized histogram, we find an optimal threshold t star, for example, equals to 3. Using this t star, we can dichotomize pixels into two classes, C0 and C1. Before to talk about the used class separability measure for determining the optimal threshold t star, we firstly introduce 3 statistical terms. The first one is class occurrence probability. Let C0 of t denote pixels with gray level less than or equal to t, and C1 of t for those that larger than t. Then define P0 of t and P1 of t as the class occurrence probability of C0 of t and C1 of t respectively. For example, P0 of t equal to 3 is the class occurrence probability of C0 of t equal to 3 and equals to 0.6. Similarly, P1 of t equal to 3 is 0.4. The second statistical terms are class means for C0 of t and C1 of t, and are denoted as mu0 of t and mu1 of t respectively. Class mean is the average of grade values in a class. They are calculated by taking normalized summation of all pixels and divided by class occurrence probabilities. For notation simplification, we denote these two terms in red and green circles as Q0 of t and Q1 of t respectively. The less statistical terms are class variance and are denoted as sigma 0 square of t and sigma 1 square of t. It is a measure of the spread between grade values of pixels in a class. They are calculated by taking the difference square of all pixels to the class means and divided by class occurrence probabilities. Here shows an example to compute the class means and the variance of class C0 of t equal to 3. For class mean, we firstly compute the normalized summation and then divided by class occurrence probability. It equals to 1.67. For class variance, we firstly compute the difference square of all pixels to the class mean and then divided by class occurrence probability. It equals to 0.22. After introducing these three statistical terms, we next talk about the class separability measure used in O2 algorithm. According to observation, pixels in the same class should be with homogeneous grade levels. Therefore, grade level homogeneity can be used to measure the effectiveness of a class. Variance is a good and widely used metric for measuring homogeneity. Low variance means high homogeneity and vice versa. Accordingly, within class variance used in the discriminant analysis can be applied to evaluate the goodness of a threshold T. What is within class variance, denoted as sigma W square? It is defined as the weighted sum of class variance. The weights are the class occurrence probabilities of all classes. The better the division T is, the lower the within class variance sigma W square is. Accordingly, the selection of optimal threshold T star is to minimize the sigma W square subject to the condition that none of classes are empty. For example, when T is 0, this division is invalid because class 0 is empty. When T is 1, the sigma W square is 2.5. After computing within class variance for all threshold values, the optimal threshold T star is the one with minima within class variance that is 0.75. Thus, T star is 2 or 3. Because we have to compute the class variance in within class variance, it is a second-order statistics and hard to compute. Therefore, O2 algorithm use between class variance as class separability measure. what is between class variance denoted as sigma b squared of t? It is defined as the product of two class occurrence probabilities and the distance square between two class means. According to statistics theory, global variance sigma g squared of an image is a constant and equals to the sum of within class and between class variance. Consequently, minimize sigma w squared equals to maximizing sigma b squared of t. So, the objective functions thus becomes maximizing between class variance sigma b squared of t. Because we have to compute the class means in between class variance, it is a first-order statistics and easy to compute. After introducing the class separability measure in O2 algorithm, we next detail the O2 algorithm to find the optimal threshold T star. In initialization step, we firstly declare and initialize 6 variables. The first 4 variables are for computing between class variance. At initial, we consider class 0 is empty and all pixels are in class 1. Thus, P0 is set as 0.0 and P1 is set as 1.0. The variables Q0 and Q1 are for recording the normalized sum of gray values of class 0 and class 1 respectively, and are also initialized accordingly. The last 2 variables T star and sigma max square are for recording the optimal threshold and the maxima between class variance that we explore so far, and both are initialized as 0.0. During iteration stage, T goes from 0 to L-1 and there are 5 steps in each iteration. At step 1, it updates the 4 statistical variables in a recursive manner. That is, the computation of the variables at current iteration is based on those at the previous iteration. So what we do at each iteration is to move the pixels with grade level T from class 1 to 0. Accordingly, at step 1, we add little pt to P0 but subtract pt from P1, and similarly for Q0 and Q1. At step 2, we check P0 and P1. If P0 or P1 is 0, we proceed to the next iteration immediately. At step 3, we compute 2 class means mu0 and mu1 respectively. Next, we compute the between class variance. Finally, if the current between class variance is larger than or equal to sigma max square, we update T star and the sigma max square accordingly. To describe the O2 algorithm in more detail, we use the aforementioned example for explanation. Here shows the initialization step for the above example. It is noteworthy that all pixels are initially considered as class 1. Therefore, Q0 is set as 0, and Q1 records normalized the sum of gray values of all pixels and is initialized as 3. At iteration 0, we move the pixels with grade level 0 from class 1 to class 0. Since little p0 is 0.0, so these 4 statistical terms remains at their initial values after step 1. Hence, we proceed to the next iteration because class 0 is empty, that is p0 is 0.0. At iteration 1, we move the pixels with grade level 1 from class 1 to class 0. The ratio of pixels with grade level 1 is 0.2. Accordingly, we add pointer 2 to P0 and Q0, but subtract pointer 2 from P1 and Q1. Because class 0 and class 1 are not empty, we skipped the step 2 and directly go to step 3. At step 3, we compute the class means, and at step 4, we compute between class variance. At step 5, because the sigma b square of t equal to 1 at current iteration is larger than sigma max square, so we update t star to 1 and sigma max square to 1.0. Then we process iteration 2 and update t star and sigma max square. Process iteration 3 and update t star and sigma max square. After completing iteration stage, we got the maxima between class variance 2.66 and the optimal threshold value 3. Using this obtained optimal threshold, we can threshold the input image into binary levels. In this lecture, we detail the O2 algorithm, which is a method to find an optimal value for global thresholding. Thanks for your listening and have a nice day.